eigenvalues, right? The eigenvalues has to be less than 1 in its magnitude. But the matrix doesn't just have one eigenvalue, it has two eigenvalues, right? So how can we impose the stability criterion? Is that one of them has to be having a magnitude less than 1, or both of them, or average of them, or what is the criterion? Both of them, right? I mean, we have already seen a case when we have this third order scheme where we have a matrix, one eigenvalue is 1, the other is 0.1, the other is -2, and the scheme is unstable. So as soon as one eigenvalue exceeds magnitude 1, we are going to have trouble. So all of the eigenvalues have to have its magnitude less than 1. Or I should say that the maximum possible absolute value of eigenvalue of the matrix A, right? 2 lambda delta t, 1, 1, 0, has to be less or equal to 1. That's the criterion. All right. So, but now it's a little bit tricky to figure out, right? So, what is the eigenvalue of this matrix? And this is just something slightly more difficult than forward Euler, and we are going to encounter schemes that are even more difficult than that. So how do we figure this out? Usually we figure out numerically. I mean, one of the insights is that the stability actually depends on lambda delta t, not just the lambda itself. Which means if you decrease delta t by a factor of 2, my stability region is going to expand by a factor of 2, right? Automatically. So just like in forward Euler, right? If I decrease delta t by a factor of 2, my stability expands by a factor of 2. If I increase delta t by a factor of 2, my stability region shrinks by a factor of 2. So that's going to be automatic. So we only need to consider, for understanding the stability, we only need to consider the case when delta t is equal to 1, right? Because if delta t is equal to 0.1, I know just expand everything by a factor of 10, and I get the stability region. So let's just consider the case when delta t is equal to 1. Okay, and for this case, we just have 2 lambda here. Now let's go into MATLAB and let's actually go to our lecture 6 folder, and let's figure out what is the stability region for midpoint. For this, I'm going to make a grid of lambdas. So a real lambda, let's do a link space of -2 to 2. I'm going to make let's do 1,000 points. Okay. Imaginary of lambda is going to be the same, link space of -2 and 2. And I think what's the function that makes I think mesh grid is the function that takes a real lambda and the imaginary of lambda, right? That makes a it's too much. It makes a 2-dimensional matrix that that is going to give me all the possible combinations. So I'm going to assign it, I'm going to overwrite the same variables. Okay, so now if you look at the workspace, my real lambda is going to be 1,000 by 1,000. So on the vertical, on each column is the same number, but different columns have different numbers. Well, if you look at imaginary, okay, I think I had a typo. Yeah, if you look at oh, that's bad idea. I had the real lambda being already huge. How do I stop it? Anybody knows where is the stop button? Oh, okay, it's good. Okay, let's do it again. Real lambda, imaginary lambda is equal to this, and this one doesn't have the typo. Okay, so I have the real lambda changes in the different columns, and the imaginary lambda is the same for every row, but it changes over the rows, right? So then let me just say lambda is equal to real lambda plus imaginary lambda times 1j. Okay, so then I have a lambda that is a 1000 by 1000 matrix, and the real part is the changes along the columns, and the imaginary part changes along the rows. So let's figure out what is the maximum eigenvalue of this matrix. Okay, so let's just write a simple code to do that. The script midpoint. Okay, we are gonna be, for I goes from 1 to the is it size of lambda in the one dimension, right? So if you type size of lambda in the first dimension is 1000, in the second dimension is also 1000. Okay, and j is equal to size of lambda in the second dimension, and I'm going to close the loop. So I have a matrix that is going to be what? 2 times lambda ij, and I have 1 and 1 0. Okay, and I want to compute the maximum eigenvalues of this matrix. So let's say a is equal to, if I type eigenvalue of a, it just gets me the values, and if I type the absolute value and I take the max, it gives me the max, right? So what I want is this guy, and I'm gonna store this in a new array. It's called max eig apps. Let's just say this is gonna be zeros. Well, let me just say lambda times 0, so that it has the same size as lambda, but all zeros. Let me just make sure it's a real array instead of a complex array. So max eig apps I and j is going to be equal to this, right? So let's run it. Takes a while. It's doing eigenvalue calculation of a million matrices, and now it's done. Now I have this, where is it? I have this max, wait, where is, oh, my workspace. I have this, where is it? Oh, max eig apps, right? I have the magnitude. So you can see clearly, if I have 5 point something, unstable, right? If I have something less or equal to 1, then it's stable. So how do we figure out? Let's actually plot it as a surface.